Okay, good morning to all of you. In previous session, we discussed analysis of discrete time, linear time invariant systems. Okay, so there we have discussed two methods for identifying the response of the given DT-LTI systems. Okay, so the first method is identification of solution of the given input-output equation, that is nothing but the difference equation. Okay, so the difference equation is used to represent the response of the system by using the combination of inputs and outputs. Okay, so we are identifying the solution, that is total solution of the given difference equation comprising homogeneous and particular solution to get the response of given DT-LTI system. Okay, so second method is where we are representing the given input x of n by using some elementary discrete time signals. Okay, so where we will be decomposing input as the combination of elementary discrete time signal, and then we are identifying the response for those each elementary discrete time signal, and then by taking its linear combination of those outputs of elementary discrete time signal, we are identifying the total response. So that is nothing but the convolution summation that we are applying there. So in today's session, we will be discussing how to identify the response of DT-LTI system to arbitrary inputs by using convolution summation. So today we'll try to derive the formula for convolution summation, right? So the response of in convolution summation, we are using the elementary discrete time signal, that is nothing but del of n. Okay, del of n is nothing but the unit sample signal. Okay, so we are trying to identify the response of DT LTI systems, okay, for given input, okay, by using convolution summation. Okay, so basically here we are using the elementary discrete time signal del of n, which is nothing but the unit sample signal. Okay, so the response of this unit sample signal to the response of the given unit sample signal, if you are applying it to the discrete time system, okay, so that response is represented as h of n, okay, which is also called as impulse response. Okay, so it is called as impulse response, right? So h of n is the response of system when you are applying del of n as an input to the system, right? So the system, if we try to delay the impulse response by k sample, okay, if you are talking about time invariant system, right? So we are saying in the time invariant, when we are saying the classification of system, there we are saying the time invariant and variant system. Okay, so if x of n is the response of the system, then sorry, x of n is the input to the system given to the system capital T, and y of n is the response of system. Okay, then if you are applying x of n minus k to the given system, then that response should be y of n minus k. Okay, so what we're trying to do there, so if the system is time invariant, then the response of system can be directly identified by delaying the output by k samples. Okay, if it is time invariant variant system, okay, so that response will be y of n comma k. Okay, so this y of n comma k was the response of system when you are applying x of n minus k to the system. Okay, and if it is equals to directly the delayed version of the output, okay, y of n minus k is nothing but delayed output. Okay, so if both are equal, then you are saying that the system is time invariant. Okay, so these things were already discussed. Okay, these things were already discussed when we have seen the classification of system. But now if you are applying to this system this delayed version of the unit sample signal, okay, then that response can be represented as h of n comma k, right? But if it is time invariant system, okay, so this response will be equals to what? H of n minus k, right? Simply as h of n is the response, that is impulse response of the system when you are applying unit sample signal to the given system, right? So if it is time invariant system, then that response will be simply you are delaying the impulse response by k samples, okay, when you are applying the del of n minus k to the given system, right? So here again this small n is nothing but the discrete time, okay, discrete time unit, right? And k is the parameter showing uh, by how much amount you are delaying the input signal, that is del of n in this case, okay, that is delay or shift parameter, you can say shift parameter, okay. So we are delaying the uh, unit sample sequence by k samples, right? So this is nothing but your unit sample sequence, right? Its response is represented as impulse response h of n. If you are delaying that unit sample signal by k samples, then your response will be denoted as h of n comma k. But if it is time invariant system, then that response can be represented as h of n minus k. Okay. Now we consider here the input x of n. Okay, because we are moreover interested in identifying the response of system. Okay, for the input x of n. So x of n, if we feed to the system capital T, right, then it will produce output y of n, right? But as per that second method that we had discussed in the previous session, this input x of n can be represented as the by using this elementary discrete time signal del of n. Okay, we will be using del of n to represent the given input signal. So how it can be represented? So x of n can be represented as summation k. Okay, so here I will represent x of k into del of n minus k, and k can be minus infinity to infinity. Okay, so see, here I am representing given input signal x of n by using elementary discrete time signal del of n. Okay, by multiplying x of k with the uh, delayed or the shifted version of del of n, right? So we know that del of n is 1. Okay, del of n is 1 for n is equals to 0, right? And it is 0 otherwise. We know this functional form of the unit sample signal, right? So it is unit sample signal. Okay, so this equation will exist. Okay, this equation will exist when this term is 1. Okay, so when this term will be 1, so when you will substitute, when this parameter passed to this del is 0, right? Because if n is equals to 0, then and then only, that is del of 0 is 1 only, right? And for other values of n, it is 0 basically. Okay, when you are substituting 0 to this function, inside this function, then it is 1, otherwise it is 0, right? But when this value will be 0, so when you are substituting k is equals to n, right? So that means this complete term or complete equation will be non-zero only for n is equals, or sorry, k is equals to n. Okay, if you are substituting k is equals to n, okay, so what will be this equation? If you are substituting k is equals to n, so it will be x of n multiplied by del of n minus n, right? Del of n minus n, we have substituted k is equals to n here, so therefore it will be x of n multiplied by del of n minus n. So del of n minus n is nothing but del of 0, right, multiplied by x of n, and this will be simply equals to, because del of 0 is 1, so this will be equals to x of n. And we know that this complete equation will exist for k is equals to n only. If you are substituting any other value of k, so del of n minus 1, del of n minus 2, del of n minus 3, right? So it will have 0 value. Okay, this term will have 0 value for negative and positive values of k, except k is equals to n, this term will be 0. As this term will be 0, 0 multiplied by x of k will be 0. Okay, So simply this equation represent x of n. Okay, we are representing x of n in terms of this elementary signal, right? So that is how we are decomposing the given signal, input signal x of n, by using the elementary discrete time signal, that is unit sample signal in this case. Okay, now we want to identify the response of system. Okay, the response of system means we are identifying y of n. So we will be giving x of n as input to the system, but in this case this input x of n now represented as this combination. Okay, k is equals to minus infinity to infinity x of k into del of n minus k. Okay, so again in this case this summation k is equals to minus infinity to infinity x of k can be termed as here as not the input that can be passed to the system, because to the system we are giving only the inputs which present the actual discrete time of system. Okay, so small n is the time interval which is used in the system, so therefore we'll be feeding del of n minus k to the system, right? So here this y of n can be simply identified as y of n is equals to summation k is equals to minus infinity to infinity x of k into, here we are seeing if you are giving del of n minus k to the system, then its response can be represented as h of n comma k, right? So here I can replace this t of del of n minus k as h of n comma k. Okay, that is nothing but impulse response of the system for the input del of n minus k. Okay, so this is for what, this equation. Okay, I will rewrite this equation in next slide. Okay, so here y of n is equals to what response you got here, k is equals to minus infinity to infinity x of k, right, into h of n comma k, right? So this will be the response of, this is the response of linear time variant system. Okay, linear time variant system. But if system is time invariant, okay, so if system is time invariant, so in that case this response can be represented as, instead of h of n comma k, you can use directly h of n minus k, as we have seen in the previous slide, right? So if it is time invariant system, as per time invariance property or shift invariance property, you can directly identify that response as h of n minus k. Okay, so the response of system for del of n minus k will be h of n minus k if it is time invariant. So this is for what, linear time invariant system. Obviously it is discrete in nature. Okay, it is discrete time system, but the response of linear time invariant system can be identified by using this equation. Okay, so instead of h of n comma k, we can directly write h of n minus k, right? Correct. So that is the response of linear time invariant system. So this formula, okay, this equation is also called as what, convolution summation. Okay, and it is the formula for convolution sum. Okay, so this is the formula for convolution summation. Okay, so formula is simply y of n is equals to summation k is equals to minus infinity to infinity x of k into h of n minus k, right? So for identifying the response of system by using convolution summation, you will be using this equation, okay, or formula, right? So we can compute this convolution summation graphically or by using, there are various methods, okay, to compute this convolution summation. First one is by using graphical method, second one is the matrix method, third one is the tabular method, fourth one is mathematical. Okay, So we'll be going into details of each one of these methods in subsequent session, how to identify the convolution summation. Convolution summation, why we are using convolution summation? So obviously to identify response of the system. Okay, that means for analyzing the given discrete time, linear time invariant system. Okay, correct. So by using convolution summation, you can identify output y of n of the system. So for identifying convolution summation, we'll be using any one of these methods: graphical methods, graphical method, matrix, tabular, or mathematical, directly using the convolution summation formula. In most of the books, these two methods are given as same, but these are two different methods. Okay, you have to keep in mind matrix method and tabular method are different. Right. So we'll be going into details of it in next sessions. Right. But computing the response, y of n of the system by using convolution sum involves various operations. What is the formula for it? So y of n is equals to k is equals to minus infinity to infinity x of k into h of n minus k. Right? That is the formula for convolution summation, and how it is derived. So we are represented in this previous presentation. Okay, we are using impulse response del of n. Impulse response for input del of n is represented as h of n. If you are delaying that impulse unit sample sequence, okay, del of n by k sample, then its response will be h of n comma k. In time variant system, in time invariant, it will be h of n minus k as time invariant property, right? And here what we have done, we have represented input x of n by using the impulse response, unit sample sequence, okay, elementary signal del of n. So here we are multiplying x of k with del of n minus k. So we use this elementary discrete time signal, okay, del of n to represent the input x of n. Okay, we decompose input x of n by using this elementary discrete time signal. So this equation will exist only for k is equals to n, because for k is equals to n, this term will be 1, otherwise it will be 0. So if you are substituting k is equals to n, so it will be simply x of n. Okay, if you substitute any value of k here, and after adding all these values, you will get simply x of n. Okay, as an what solution of this equation, right? So now we are applying to the system this input x of n. The response will be represented as y of n, but we are represented x of n as the combination of this elementary discrete time signal. So we'll be replacing x of n with maybe k is equals to minus infinity to infinity x of k into del of n minus k. But the system term is only input term is del of n minus k. So we have taken k is equals to minus infinity to infinity x of k out of system, and to system we have applied only del of n minus k. So when you are applying del of n minus k to the system, then the response will be represented as h of n comma k. In case of time variant system, but it is time invariant system, then it will be h of n minus k. So this is how we are derived the convolution formula. Okay, but computing the response y of n by using convolution sum. Okay, we are computing the response of the system by using convolution sum. So convolution sum formula, y of n is equals to k minus infinity to infinity x of k into h of n minus k. So it comprises various operations. So basically it involves 4 steps. Okay, so first one is folding. Okay, because you will be provided with input x of n and h of n, okay, which you will be representing as x of k, okay, simply, and h of k. So x of n and x of n, x of n and x of k are same. Similarly, h of n and h of k will be same, right? So by using x of k and h of k, so x of k is taken as it is, but h of k has been folded. Okay, so h of k not taken as it is initially folded. So you identified h of minus k from it. So initially it will involve folding operation. So first step is folding. So you will be folding. So fold h of k about origin. Okay, about k is equals to 0 to obtain what h of minus k. So that is the first step. Okay. So if you are identifying it by using any one of these methods, so you are using these four methods, any one of these four methods to identify convolution summation. So these four steps will be common in all of those methods, right? So you are initially performing folding on given impulse response h of k to get h of minus k. Then second one is the shifting. Okay, shifting operation. So you are shifting this h of minus k by n sample. Okay, so you are shifting it by n. So this again, n can be negative or it can be positive, right? So shift h of minus k by n to the right. Okay, so when it will be shifted right, or you can shift it to left, okay, depending on value of n, whether it is positive or negative. So it will be shifted to right if n is positive, okay, or it will be shifted to left when n is negative, right? Okay, so that will to why we are shifting it to obtain h of n minus k. That is the second step. First step was folding, second one is shifting. In shifting you are shifting h of minus k by n sample. So h of minus k is the folded version of h of k, so it is shifted by n sample, so it will be shifted to right, okay, or it will be shifted to left depending on value of n. So if n is positive, then it will be shifted to right, okay, and if it is negative, so it will be shifted to left, okay. Then third step is the multiplication. So you are multiplying what, x of k and h of n minus k. So in multiplication you obtain h of n minus k. You already have x of k. X of k is nothing but your x of n, but this x of k will be multiplied with the h of n minus k. Okay, so that is the next step, that is nothing but multiplication. And the last step is the summation. Okay, so fourth step is summation. So you will be summing all these values of product term, that is x of k into h of n minus k, over this limit, that is k is equals to minus infinity to infinity. Okay, you are summing all these values which you have obtained at the product terms, right? So this is how you will be performing the convolution summation, which involves folding, shifting, multiplication and summation operation. So to summarize, your convolution summation can be identified as summation k is equals to minus infinity to infinity x of k into h of n minus k, right? And it involves four operations, that is first one is folding, okay, second one is shifting, third one is multiplication, and fourth one is the summation. Okay, so this is how the convolution summation can be used to identify the response y of n of the given discrete time linear time invariant system. Okay, so in next session we'll be using this convolution summation formula to identify the response of the linear time invariant system. Okay, so thank you for joining this session.